Okay, continuing with optics. Now, I looked at the schedule. Today was supposed to be talking about diffraction, where we play with these things and have a lot of fun with them. But I haven't talked about telescopes and microscopes yet. So we talked about the eye yesterday with I spelled them all, the common mishaps with the eye. For the test, you need to know what these are and how to correct for them and be able to calculate the correction based on a person's, near point, far point. So let's review just real quickly which one is a problem for somebody that has myopia, the near point or the far point. They're nearsighted, so their problem is the far point. So your calculations for prescription are going to deal with the far point if they have myopia. What's the problem with hyperopia? That's a near point. That's a person who is farsighted. They can see far just fine. Their near point is too far out. Myopia, the far point is too close in. What is the ideal far point? How far should you be able to focus? Infinity. What is the, quote, ideal near point? 25 centimeters. Okay, David, you were wearing your contacts yesterday. What did you measure for your actual near point?
I think it was somewhere around 13, 16.
Somewhere around 13 or 16. So they corrected his vision to give him better near point than what we consider ideal.
Yeah, 16.
And that's good, right? It's good to be able to see things closer. And we'll see a reason why in today's lecture. People who are farsighted, believe it or not, they can, quote, focus on things behind their head. Now, when I say that, it sounds wrong, right? You just look at Sarah's face and you know it's wrong. Remember our example with this, where I brought it up and Anna could not see her face. It just was, a big flesh tone. But Claudia behind her could. And I said it's because the image is forming behind Anna, but in front of Claudia. Well, if you are farsighted, you can actually focus a little bit on light that would have, it's that the image being farther than infinity away. And so you could actually have seen a little bit of that, which is crazy. Presbyopia. What's the problem with presbyopia?
It's the hardening of the lens. Is it the cornea?
Not the cornea, of the crystalline lens.
Crystalline lens.
Remember, the cornea is the primary focusing element. The crystalline lens is the one that adjusts so we can accommodate, so we can focus on different distances.
The lens is like behind, right?
Yes, the lens is behind the iris. And so when that hardens, you can't accommodate as much and you can't adjust your focus. And so you start to have the symptoms of hyperopia, that is, your near point moves out, but unlike with hyperopia, your far point doesn't move out as well. And so you could have presbyopia along with myopia, and then you just have a very limited range that you can focus. That's when life is bad, and you need bifocals. You have a question, sir?
Hardening of the lens. Sorry, hardening of the cornea.
Hardening of the lens, not the cornea. And then what's astigmatism?
That's like focusing on
And-
one thing on the others.
It's an asymmetry of the cornea so that you have a different focal length for light that is in this plane compared to light that is in this plane, just using an example of two perpendicular directions. So astigmatism is corrected with an asymmetrical lens. Presbyopia is corrected with bifocals or continual gradient lenses. Hyperopia is corrected with converging lenses. Myopia is corrected with diverging lenses. One thing I didn't talk about that I intended to, I talked about eyeglasses and said that the eyeglasses, unless told differently, put them at 2 centimeters in front of the eyeball. And that changes the object distance and image distance compared to the lens. It's not the same as the position of the object compared to the eyeball. What would be different if instead of using eyeglasses, you used contact lenses?
There's no 2 centimeter difference.
Yeah, there's no 2 centimeter distance. Is that going to change your prescription?
Maybe not.
Yes, it will. Because remember, the prescription was power is equal to 1 over f, which according to our thin lens equation, 1 over distance object plus 1 over distance image. So if distance object and distance image are shifted by 2 centimeters, so is the power. I mean, this power is not shifted by 2 centimeters, but it's also shifted. So your contact prescription is not the same as your eyeglass prescription. Today we're going to talk about simple magnifiers, telescopes, and microscopes. Although I have the order of these two reversed. We'll talk about microscopes first, then telescopes. So angular magnification is the first thing we need to talk about. When you look at something, well, let's take a common thing that is, I can't remember the word now. Sometimes I just lose words. Visual confusion. When you look at the moon and you judge how big the moon is, if it's up here in the sky, how do you determine how big it is? By looking at it, but your brain says big or small. And how does it make that assumption or that determination?
How big it appears to you.
Okay, how big it appears to you. If you don't have a reference thing like a tree nearby, then without a reference, all your brain can do is say, well, it takes up this much of an angle on the retina. This much of the retina is taken up by it. And so in reality, before our brain gets involved, we measure the sizes of things by the angular size, how big the angle is that it's making. And so when we talk about magnifiers, we're going to talk about magnifying the angular size. So when you look at the moon and it's up in the sky, you have nothing to compare it to. And it looks, well, about as big as your finger at arm's length. Now, if it's down the horizon, suddenly you have things to compare it to. Things like houses or trees. And what happens to people's perception of the size of the moon when it's on the horizon? They tend to think that it's bigger. They think it's bigger because it's down here on the horizon. They know that's a big tree. And look, the moon is bigger than that tree. And so there is a common optical illusion. That's the word I was using. Optical illusion, people think that the moon is bigger when it's on the horizon. Now, there is another thing that's associated with this. Have you ever looked at the sun as it's setting and noticed that it changes shape?
Mm-hmm. It seems to get flatter, right?
Yeah, it seems to get flatter. It goes like, why? Any idea why? Right? We're scientists. We have that whole scientific method. You observe something interesting. The sun appears to get flat when it gets on the horizon. Come up with a hypothesis. Why?
Isn't it due to the diffraction between the vacuum and the atmosphere?
Okay.
Or not the diffraction, but the refraction.
Refraction is the right word. That's the actual answer. The Earth's atmosphere, of course, has a speed of light that's slower than vacuum. And so when light from the sun comes into the Earth's atmosphere, it bends toward the normal because it's going to something slower. So when the sun is down on the horizon, light is coming, it hits the atmosphere like this, and it bends down that way, right? So the result is we see the sun not at the right place when it's close to the horizon because of that refraction. And the sun actually sets, when we see the sun go below the horizon, it's actually about 5 degrees below the horizon already. So sunrise to sunset, as we observe it, is not the same as sunrise to sunset in actuality because of that diffraction. Now, that was not part of my goal for today. It was just something interesting, relevant to today. So the key here is we measure sizes with the angle that the object makes with our eyeball. Oops. Using a different app so I can zoom in on pictures.
Can you actually go back to the other slide?
To this one?
No, to the enlarged. I'm just looking at the enlarged. So the apparent size of the object. What's that image? Formed on the retina. So, what does that mean?
To us, it's enlarged. The next slide shows the picture to explain that. It's enlarged if it makes a bigger angle. So this is showing the same object at position 1 and position 2. When the object is closer, then it's going to make a bigger angle. Right? If I take my finger and I hold it out here, the tangent of the angle is pretty small. When I bring it up here, the tangent of the angle made between my eyeball and my finger is much bigger. And so my brain says, wow, my finger's bigger. If I didn't have anything to compare, I would actually believe my finger's bigger when it's close to my eye.
Like if we did the geometry of it and we were like the tangent of this from here, this is smaller and this is bigger.
Yeah. And so, I mean, it has the dashed lines there are showing you the angular size when it's far away.
Yeah.
And then the solid blue lines are showing the angular size when it's close. And clearly the angle is bigger for close than it is for far.
Okay, it's just because of the geometry. That makes sense.
Just because of its position. That's why some of those optical illusions you see, like you have a house and the house has a checkerboard pattern on the floor and the roof slopes down. So at one side, it's like 3 feet tall and the other side is like 9 feet tall. You guys ever seen that kind of optical illusion? You have somebody stand here close to somebody far away and you're like, wow, the person in front of me is so much bigger than the other one. Then you have them trade position, they change size. It's because your brain is doing interpreting based on the other things around it and not just the angular size. If you had none of that, your brain would say, smaller angle, bigger angle, this one's bigger. But it's comparing to other things. So our brain is very active in our true judgment of size unless we don't have a reference. So this is just words. Let's get to our first woo clap question, which I alluded to in class yesterday, kind of. What do you naturally do when you want to see something in greater detail? Answer all that are true for you. Should get one more answer here. Maxwell is not in here, so we're not waiting for him. All right. Right at the last second, we got our last answer. 9 people said move it closer to their eyeball. 1 person said move it farther from their eye. What did you say, Max? Okay, so Max didn't read the question yet. So we had answers for all of these. Now, 2 of these don't make sense. The 2 that don't make sense are actually blinking rapidly, depending on the situation, could be helpful, right? If your eyes are dry or something, I don't know. I'm not going to stop blinking and blinking rapidly, depending on the person. Either one might help them see a little better. Decreasing the ambient light is just not going to help. And moving it farther from your eye shouldn't help unless you're farsighted. And so those are the ones that I expected to not be answered. The other ones, increase the ambient light, that is going to help. It's going to help because we talked about yesterday, there's a physiological response. That iris is going to close down, make it a smaller pupil. And with the smaller pupil, you have a better resolution. You can see more detail because it's better focus if your focus isn't perfect. Now, if your focus is perfect, it doesn't help. But who has perfect vision? Oh, man. Okay, that's true. Squinting. We talked about squinting. If your vision is not perfect, that can help your resolution again for the same reason as increasing the ambient light. The one that everyone answered and that is the one that the textbook has is you move it closer to your eye. Why? Because it's going to give you a bigger angle. So we're going to talk about angular magnification as the ratio between the angle you would have normally seen and the angle you get with an assist. So with the example with the picture that I was talking with Claudia about, we had something far away, it makes this angle with my eye. I bring it to here, it makes this angle with my eye. The angular magnification is the new one, the one that's improved, divided by the original angle. So we have that in equation form right here, an equation that's the size of, Texas. Magnification, this is angular magnification, is the angle that it makes when you have your aided device divided by unaided. So let's get into this.
Wait, could you scroll back up to that quick?
Good?
Yeah.
So the maximum angle that you can get without anything special is what we're going to use for the unaided angle. So I use an example of taking the pin at arm's length and bringing it up here. We're going to take for our theta unaided the angle it makes at the closest distance where it's in focus. So in terms of geometry, when I bring it to that closest distance where it's in focus, here's my object, here's my eyeball. If it's at the closest position where it's in focus, what is this distance? By definition, that's the near point. So I put N here for near point. Don't be confused about the N. Usually I put NP, but I'm using N now. Here's the height of my object. And so the angle that it makes with my eye, well, what trig function relates opposite and adjacent? I know, it's a trick question. So I have tangent of theta, and that's theta unaided, is h over n. Now I'm going to leave it at that for another couple slides, and I'll come back to that equation. Another couple slides because I have this. If I use a simple magnifier, just a simple lens, which I should have one right. I put them away. Oh, no, here it is. Here I have a simple magnifier. I can use this so I can take something, bring this as close as I can read it carefully, bring it up here, and I can bring it closer. Woo! Bring it closer. It's going to make a bigger angle with my eye. And so I can see it more clearly by using my simple magnifier. Oh, I smell this monocle. So the simple magnifier, the whole point of the simple magnifier, like, Grandma used to use to read the newspaper, is so she can bring it closer to her eyeball and thus have a magnified size that she sees. And for all of our trials, for all of our work, we're going to assume that they hold the magnifier up next to their eye. Obviously, they don't always. Sometimes they do it like this. But we're just going to make that assumption to make it as simple as possible. Now, coming back to this, remember I drew this picture. We did the calculation. We said tangent of theta was equal to the height over the near point. But if it's a small angle, and you know what? If we're trying to magnify things, it's going to be a small angle. We don't try to magnify things that make big angles with the eye. So for small angles, tangent theta in radians is approximately equal to theta. And so we can say that this tangent theta is approximately equal to theta. So the theta unaided is the height of the object divided by the person's near point. Makes sense, doesn't it? Yes? So now we're going to use a magnifier. Now we're going to take an object, and using my simple magnifier, I'm going to start by bringing the object to the place that is the easiest for viewing. The easiest for viewing is when the image is at the far point. So this is my example of, this is the farthest point where I can focus on it using this magnifier. In that case, I said, where's the image? At the far point. But if the image is at my far point and I have perfect vision, where's my far point? Infinitely far away. So the image is infinitely far away. if I'm going to have an image distance that's infinity, what is the object distance? If I have the distance the distance of the image at infinity, then what is the object distance?
Focal length.
Yes, because 1 over infinity is 0. And so I have 1 over f is 1 over distance object. So the object is a distance away of the focal length. For this, we call this unaccommodated viewing. Unaccommodated means that the eyeball is relaxed and I'm just looking at something at my far point. So for unaccommodated viewing, I'm going with the spelling I was given yesterday. For unaccommodated viewing, then the aided angle, we're going to have the same height of the object, but now it's a distance of a focal length away. Now you might say, wait a minute, it's the angle the image makes, not the angle the object makes. And you might add a few more U blank. But remember the rays, the vertex ray goes straight through. And so the image is going to be formed somewhere along this ray. Hence, it still is correct. Because the image will be somewhere, it'll just be out at infinity like that. So the simple magnifier with unaccommodated viewing, we have the thetaed angle, the accommodated angle, the aided angle is the height of my object divided by the focal length of my lens. So to find the magnification, I just combine those. Magnification is the aided angle divided by the unaided angle. So the aided was h over f, the unaided was h over n. Of course, the h's are both in the numerators. So we cancel those h's. 1 over f divided by 1 over n. Do the whole invert and multiply rule. And that's n over f.
Or n
N is the near point.
And f.
And unless told differently, you just put in 25 for that. And f is the focal length of the lens I'm using for the magnifier. Now keep in mind, do I want a convex or a concave lens for this?
Should be a convex.
Do I want converging or diverging? So you can look at the picture or something else? Because the picture tells you the answer.
Convex. Yeah, convex.
I need a convex. I need something that's converging because the diverging image, the actual focal point would be on this side. And
So the only way to get like the 1 over PHYS 0 is for the simple magnifier convergent lens, right?
yeah. Okay, so this is for a converging lens. We have to understand that was implied, but you have to have it. You can't say, oh, any lens, diverging will work too. It doesn't. Yes?
Okay, so it's not that angular magnification is for converging lens, but the problem you gave us for converging lens. Like, so long.
No, the angular magnification is for converging
It's
lens.
always for
Yes.
converging lens.
Well, the equation theta aided over theta unaided is generic.
Okay.
But for the simple magnifier, it's always converging lens.
Angle, so the angular, so the angular magnification for a simple magnifying lens is always converging.
Yes. And so there's the magnification you get for unaccommodated. Remember, this was unaccommodated. What did that mean? Thank you, dictionary. Without accommodation. With regards to the eye, what does that mean? Yes, that the lens is not there, but relaxed. It's not working. So your eyeball is relaxed. You don't get eye strain in that case. But what if you wanted eye strain? What if you wanted to bring it as close as you can? Remember, I brought this up and I said, okay, here it's in focus. So that's the farthest it could be. but it's still in focus all the way up to here. It's just my eyeball has to work. What's happened to the magnification if I bring it even closer? Well, before it gets blurred. It gets bigger. So I can get a bigger magnification than this if I actually use the accommodation of my eyeball. Now I have a question before we go on to that. As discussed, the object is placed at the focal point of the simple magnifier. Where is the image produced by the simple magnifier? Which goes back to why it had to be a converging lens. We have one answer, and with that consensus, yeah, we clap. Okay, Max, I expect you to answer this time. You did. I can tell you answered because the number of people went from 9 to 10. Oh, well, you're logged in at least then.
I am logged in. Oh, that's what you meant.
Yeah.
I'm logged in. There you go.
Okay, we have one person. There we go. We're all in. Here's the answers we got. Okay, this indicates we need to look back at things. Where did we put the object?
At the far wall.
The focus,
At the focal length.
which is the far point.
No, you can have different lenses. The far point has to do with the eyeball. The focal length is the lens. When we are using the simple magnifier, we put the object at the focal length so that it makes an image at one location.
So it's supposed to be.
Not the eye.
On the same side as the object. Is that what it's supposed to be?
It's on the same side as the object and infinitely far away. Right, so this is where the object is. The object is at. That's what that one was. Where the object is, not the image. The image is infinitely far away, so your eye can be relaxed, assuming that you have an infinite far point.
Can you clarify the significance of the difference between, okay, so we just did one example with the object at the near point and then one example with the object at the focal point. Is that just the difference between unaided and aided?
That was, the object at the near point was unaided. That was without a lens.
Okay.
The object at the focal length was unaided, or excuse me, not unaided, unaccommodated, but with aid of a lens.
What's the difference between unaccommodated and accommodated?
Accommodated is the one we're going to do now. Accommodated is when your eyeball is working.
Okay.
Unaccommodated is when your eyeball is relaxed.
So you use focal point if you're using a lens, and you use near point if you're using just the plain eyeball. But
That's half right. You use the focal length if it's unaccommodated with a lens.
Okay.
The near point with no lens. So you were absolutely right with the near point and no lens.
Okay.
With the lens, unaccommodated at the focal length.
So unaccommodated with the lens, we're not taking the near point into account. Like we don't.
Correct.
Okay.
Correct.
Cool.
Now we have, what if we want more magnification? We can make it so the image is at our near point. If the image is at our near point, then we have to use the lens equation to calculate where we're going to put the object to make the image at the near point. And so I have here worked out all the stinking math. The magnification aided, and this is now accommodated instead of unaccommodated, which means that our eyeball is working and we're going to make it so the image is as close as I can focus on. And so we have the theta unaided was h over the near point. The theta aided is going to be h over the distance object. But distance object, what's that? We need to move on. So using our definition that distance object, 1 over distance object is 1 over f minus 1 over distance image. I just substituted that in. And then I separate them out. I have n over f. Well, that was the magnification for unaccommodated viewing. And then I have minus n over distance image. What is distance image if I am accommodating as much as I can? Where's the image formed if I'm making the image at the nearest point I can focus on? We have a name for that. The near point. And so if I'm doing maximum accommodation, this is the unaccommodated magnification plus, well, the distance image is at minus the near point because it's the image on the wrong side. So people don't get confused about signs. Distance image is minus near point. So that's just equal to m plus 1. So
What is that for again?
that's if we are using our eye to work and get the maximum magnification we can possibly get. It raises the magnification by a factor of 1. Now, if I have a lens that has, let's say, a focal length of 5 centimeters, I'm just choosing numbers to make it easy to do in our head. If it has a focal length of 5 centimeters and my near point is 25 centimeters, what is the unaccommodated magnification? Near point is 25, focal length is 5. What's the unaccommodated magnification? 5.
Your point, yeah.
Yeah. Near point is 25, focal length is 5. Unaccommodated magnification is near point over focal length. So that would be 5. If I strain my eye, what does it go to? To 6. Now, going from 5 to 6, that is a 20% increase, right? What if my focal length was, let's say, 0.5 centimeters? Then I would go from 50 to 51. It's not worth the eye strain, right? So we generally say, it's not worth the eye strain, just use the unaccommodated and be relaxed. So in most instances, we try to design optical instruments like a microscope for unaccommodated viewing. And we use the magnification as just the near point divided by, where is it? Near point divided by the focal length. But we can calculate what it would be for anywhere in between if we use this. You know, if you have partially accommodated, let's say. But you don't get much from the accommodation in terms of magnification. Okay, a problem. Problem for you. A converging lens with a focal length of 4 centimeters is used as a simple magnifier. The lens forms a virtual image at your near point, 25 centimeters from your eye. Where should the object be placed and what is the angular magnification?
Yeah, I'm on the wording.
Is the near point like 25 centimeters?
Yes, assume the near point is 25 centimeters.
This is all you have to do for the magnification, correct?
In this case, no, because this was not unaccommodated.
It's not unaccommodated?
It's accommodated, yeah.
It's accommodated? How do you know that?
Yeah.
Because the image is not infinitely far away.
It's a minus 1?
Right. According to the words, everyone, according to the words here, what is the image distance?
25 centimeters.
virtual image at your near point, which is 25 centimeters.
Okay, the virtual image is at your near point, but that's not the right answer. Here's your eyeball. Here's the lens. Here's the image. The object is going to be somewhere like here. Nice drawing. Well, we'll go like that. Your object distance is always positive. Your image is on the same side as the object. What does that make the image distance?
3.4.
Wait, say that last part again. Why is it negative?
Because it's on the same side as the object. Right? The problem is in words. And of course, a big part of the physics is taking the description, which you can understand where the image is from the description, and putting that into the mathematical terms and how things are going to work.
And because not infinitely far away, it's accommodated.
It is accommodated. This is fully accommodated.
So it's accommodated and aided.
No, it's going to be 204 would be 7.25.
Yeah.
That's where you get the n over f plus 1 because it's fully accommodated.
Right, so it's 1 over 35 plus 1, right?
24 divided by 4
That's how it's done?
because it's 4 centimeters is the whole thing. And it's 25. And f, what's that?
I just. How do you know that? Yeah, it's 25. Oh, maybe.
DI is minus 25 because it tells us that the image is 25 centimeters away from your eye. And it's going to be on the same side as the lens, so it's negative.
And do you want it to be in centimeters or in?
Because magnification is distance over distance, as long as they're the same distances, you get the right answer. Or the same units, you get the right answer.
Negative 5. Because it was negative in the outward.
Your image distance is minus 25, so minus n over minus 25 is plus 1. Okay,
No, it'd be 25 over 1 minus.
we've talked it out with everyone. Hopefully the people in the back have been following along or doing it separately to make sure that everybody gets this. Start with your diagram, right? Here's the eyeball. Here's the lens that the problem tells us to put the lens right next to the eyeball, so all distances are measured from the eyeball lens, the same thing. It tells us that we have the focal length is equal to 4.0, I don't know how many zeros I put, centimeters. And that we have the image at 25.0 centimeters away. That's what the problem tells us. And so the first step is identifying, okay, F was easy. F was 4.00 centimeters. Distance image, we had the magnitude was 25.0 centimeters, but the sign is negative because it's on the same side as the object. And then 1 over F equals 1 over distance object plus 1 over distance image. So 1 over distance object is equal to 1 over F minus 1 over distance image equals 1 over 4.00 centimeters minus 1 over minus 25.0 centimeters. And I don't know honestly what that is.
3.45.
He says 3.45.
Because you just take the inverse of the 0.29, right?
Yeah, right. What was that? Well, did I just do one dividend? Yeah, 3.44827. So now we have the distance object, where the object is placed. That was, where should the object be placed? There's my answer, distance object. And then it asks for the magnification.
That's just 4 over 1.
Magnification is equal to n over f minus n over distance image is equal to 25.0 centimeters over 4.00 centimeters minus 25.0 centimeters over minus 25.0 centimeters equals 7.25, assuming that I can do math. N is the near point, which is 25 centimeters. Di is the image distance, which has the possibility of being positive or negative. And for every case in this, with the simple magnifier, is going to be negative. I put in a second slide just in case we needed it. Moving to microscopes. What's the point? You guys have probably all used a microscope, whether it's, in grade school or high school or even college. You will have company.
There was actually a fact because they are.
Okay. So what we got here, one person didn't get in, but I'll go with that. 1, 0, 3, 5. We have a plurality. Doesn't win an election, but you're going to make it to the runoff. Did it win this question? Small objects, definitely not large objects. The point of a microscope is to see something small. That's why we have the term micro. Micro means small. It's a scope for small things. And with the microscope, if you're going to see something small, it's got to be something that you can control as distance. If it's far away and small, you can't see it. So it's got to be nearby. So that's the point of a microscope. So you can magnify something that's nearby. Here is how a compound microscope is created. You have two lenses, one that's nearest to the eyeball. So here's the eyeball in miniature. So the one nearest to the eyeball, we call the eyepiece. We have one that's nearest to the object. We call it the objective, right? The terms are self-descriptive. Thing closest to the object, objective. Thing closest to the eyepiece. They're separated by some distance d, and then we actually adjust that distance to focus it. Now, in terms of magnification, I worked out all the math. There. So the magnification of the objective, we use the lateral magnification equation. The first one we learned. So remember that was m is equal to, it's defined as height of the image over height of the object. which is equal to minus distance image over distance object. So that's what we use, the lateral magnification for the objective. The objective is taking a real object and making a real image, and then the eyepiece is viewing that real image using the same type of eyepiece magnification calculation we just finished. So the lateral magnification is the difficult part here. Minus distance image over distance object, you just use that thin lens equation, 1 over f equals 1 over distance object plus 1 over distance image. Solve that for 1 over distance object is equal to 1 over f minus 1 over distance image, and substitute it in. And then I distributed my distance image across. Distance image over distance image, that was just 1. And distance image over focal length objective, well, I looked at my picture here. With the eyepiece for unaccommodated viewing, this image here needs to be at the focal length of the eyepiece. And so the distance for the image from the objective must be the total separation divided or minus the focal length of the eyepiece. And so this gives me the equation for the lateral magnification of the objective. The eyepiece unaccommodated viewing, we just work that out. And the total magnification is the product of those two. And so you just multiply them together. I had to get a common denominator here, so I made this f0 over f0. Because of this minus sign, it became, I brought the minus sign out, which meant I changed the signs of everything inside. So d minus focal length eyepiece minus focal length objective times the near point over the product of the two focal lengths. That's the correct equation for magnification of a microscope. So you adjust the focus by adjusting the separation between the two lenses. It's also changing the magnification a little. You will see some textbooks or some websites that drop out these two, but you really can't do that. You know, your barrel might be 20 centimeters long, but some of those eyepieces might be 3 centimeters long. 3 centimeters is not ignorable compared to 20. Notice the minus sign. What does the minus sign mean? Magnification is negative. What does that mean? It means the image is inverted. So you're seeing the image upside down, which is why when you're looking at that microscope slide and you want to see detail that's at the bottom, you have to move it down because it's actually inverted. It's really at the top, and you have to move it down to get it in the center. We will talk about telescopes Friday. Have a great Wednesday.